Hi everyone and welcome to the Learning Curve. In this video, I will be doing statistics, focusing on one sample confidence intervals for means. Confidence intervals for means is a very popular technique in statistics that is used to derive estimates of the interval within which the true population mean of a particular data set will fall. So here we are told in this problem that the volume of bottles of wine from a certain vineyard is normally distributed, which is very important. We're told it's normally distributed with a standard deviation of 10 milliliters. So this represents the population standard deviation. The vineyard's quality control manager would like to estimate the average number of milliliters, the average milliliters which are in the bottles of wine. She takes a sample of 40 bottles and obtains an average of 748 milliliters. We are asked to construct the necessary interval estimate using the 99% confidence interval. So, since this is a confidence interval for means problem, in other words, we're asked to generate an estimate of the interval within which the true population mean falls. We are going to use the formula for generating confidence intervals for means, which is x bar plus or minus z alpha over 2 multiplied by the standard deviation, which is sigma, divided by the square root of n. We were told that the data set is normally distributed, the population is normally distributed, and moreover we have the population standard deviation of 10 milliliters, and the sample size, which is 40 bottles, is greater than 30. Therefore, the conditions are satisfied for using the standard normal distribution or the Z distribution. Hence, our insertion of Z instead of, for example, T here in the formula. T-test or T-statistic distribution is used in situations where the population standard deviation is not known and also when the sample size is less than 30. So in this particular case, the conditions for the standard normal distribution are satisfied. So we're going to insert here x bar, which is our sample mean. We were told that a sample of 40 bottles obtained an average of 748 milliliters. So this 748 represents the sample mean x bar. X bar represents the sample mean. Plus or minus z alpha over 2. This is going to be the z table reading, which is based on the level of confidence of the estimate. The level of the confidence of the estimate here is 99%. And for simplicity, there are a few standard Z-table readings for different levels of confidence that you may want to memorize. For 90% confidence interval, the Z reading is 1.645. These are the most popular confidence intervals that are used in research and the most popular ones that you will find in your examinations as well. 90%, 95%, and 99%. 99%, the Z reading, the Z table reading is 1.96 and that's 95%, and 99%, the Z table reading will be roughly 2.576. So these are very, very important standardizations that will be useful for you to remember so that you can flow seamlessly when you're faced with these questions. In this case, we're asked to construct the interval estimate using the 99% confidence level. So we will use this figure. So it's going to be plus or minus this figure. 2.576 will be used to replace the Z alpha over 2 here. So here I'll insert 2.576. Because the Z alpha over 2 here just represents the Z table reading, and it assumes a two-tail situation, which is why alpha over 2 is a part of the notation. So this will be 748 plus or minus 2.576. Again, the 2.576 represents the Z table or standard normal table reading based on the level of confidence for which we are carrying out the estimate. And the level of confidence for which we are carrying out the estimate here is 99%. So we're going to get 2.576 as our reading. As I said, these are the three most popular percentages that are used for confidence interval estimates, so it might be useful to just recall these Z readings. Then we're going to insert the value of sigma. Sigma is the standard deviation of the population. Sigma, the standard deviation of the population, which is 10. So this will be multiplied by 10 divided by the square root of n, where n is the sample size or number of observations. Here it says a sample of 40 bottles were taken. So this is root 40. And then we're going to simplify this. So this becomes 748 plus or minus 2.576 rather, multiplied by 10 divided by root 40, which you could just insert that at once in your calculator and simplify. 10 divided by the square root of 40. And that will give you 1.58 rounded to 2 decimal places, 1.58. I'm just going to come up here to finish the problem. Now, in terms of order of mathematical operations, we will multiply before we add and subtract, which means that in this case, we're going to multiply 2.576 by 1.58, which gives us, so we will now have 748 plus or minus the result of multiplying 2.576 by 1.58, which to the second decimal place, that would be 4.07. So my confidence interval reduces to 748 plus or minus 4.07. This 748 plus or minus 4.07 means that I will find the lower limit of this interval by subtracting 4.07. That's how I will find the lower limit of the interval. So I'll say 748. This can be re-expressed as 748 take away 4.07 2. And to get the upper interval, I will add 4.07. So 748 plus 4.07 to get the upper value in the interval. Close that bracket. So what I will now do is to subtract 4.07 from 748, and that gives you 743.93. So that will be the lower bound of the interval. To 748 minus, so the dash there is used to mean 2 in order to represent the range of the interval. So we're now going to take 748 plus 4.07 to get the upper value in the interval. When we take 748, here's 748. We take 748 plus 4.07, we get a result of 752.07. So this is our answer. Our answer, which is the confidence interval, is 743.93 to 752.07. The interpretation of this answer would be that we are 99% confident that the true population mean, or 99% confidence that the true population mean and this is in relation to the volume of wine in the bottles. There's a true population mean volume of wine in the bottles is between 743.93 and 752.07. And that's how you would interpret it. When you're interpreting a confidence interval, you always use as a blueprint, you can just use we are whatever percentage is given in the question in terms of the confidence level. So we are, in this case, 99% confident. Then you say that the true population mean of whatever variable is in the question is between the interval that you came up with. It's important to point out here that this result here of 4.07 is what we would call the margin of error of the estimate. Once you have simplified this right-hand side here, which we did by multiplying 2.576 by 1.58, which gave us 4.07. That 4.07 plus or minus 4.07 represents the margin of error of the estimate. In other words, the estimate is really that the population mean is 748 plus or minus 4.07, which means that it could be 4.07 lower or 4.07 higher than 748, which is why we did the subtraction and addition process here to come up with the interval. And that is how we calculate confidence intervals for means. Well, hey, let's do another one to reinforce our knowledge here. So here we are told that researchers are concerned about the number of hours worked during in the Yuletide season. So researchers are concerned about the number of hours worked in the Yuletide season. That's the Christmas season. The distribution of hours worked is considered to be normal with a standard deviation of 16. So that's our population standard deviation there. As part of the study, a sample of 100 persons is taken. So that 100 persons is greater than 30. So therefore, the conditions for normal distribution would be satisfied. In addition, we have the population standard deviation. So a sample of 100 persons is taken and the average number of hours worked is revealed to be 10.25. So since this 10.25 average comes from the sample, then this would be our sample mean, 10.25. And we are asked to construct a 90% confidence interval for the true average number of hours students worked. So our formula for confidence intervals for means again is x bar plus or minus z alpha over 2 multiplied by sigma divided by the square root of n. This is the formula that we use once it is a normally distributed population that we have drawn the sample from, and we are calculating the sample size, we're calculating the confidence interval to estimate the interval within which the true population mean of the variable will fall. So this is the formula that we'll use once it's a normally distributed data set, and this will typically also be supported by having the standard deviation of the population known and the sample size greater than 30, which satisfies the conditions for using the standard normal distribution. So we'll use this formula. X bar here, which is the sample mean, is given to us to be 10.25. So we'll insert 10.25 here. That's our sample mean. Plus or minus z alpha over 2 is going to be the table reading from the standard normal distribution based on the level of confidence of the estimate. The level of confidence of the estimate is 90%. So we know, based on what I would have outlined earlier, that the z reading for 90% is 1.645. So I'll insert plus or minus 1.645 here, multiplied by sigma, the standard deviation of the population, which is 16, divided by the square root of n, and n here is 100 because a sample of 100 persons was taken. So continuing here to finish the problem, we're going to have 10.25, and this is going to have 10.25 plus or minus 1.645 multiplied by 16 divided by root 40. And for 16 divided by root 40, you can just go straight ahead and take that on your calculator. 16 divided by the square root of 40, which is 2.52. or 2.53 rounded to the second decimal place. Again, in terms of order of mathematical operations here, we're going to multiply before we add. So we're going to multiply 1.645 by 2.53. And when we multiply 1.645 by 2.53, we will get 4.16 rounded to the second decimal place. This is going to be 4.16. Remember to always multiply out this section before you add or subtract. And let's keep this going now. So we're going to find the lower limit of this interval, as we illustrated earlier, by taking 10.25 minus the margin of error, which is the plus or minus 4.16. So 10.25 minus 4.16 will give us the lower limit in the interval 2. And to get the upper limit in the interval, I will take 10.25 plus 4.16. And that will give us, so let's just write that down, 10.25 plus 4.16. And that's how we'll get the upper value in the interval. So to simplify this now, we'll get 10.45 minus 4.16 and 10.25 plus 4.16. On this side, we're going to get 14.41. That will give us the upper value in the interval. And on the other side, with 10.25, take away 4.16, we will get 6.09. So that's 6.09. So it's 6.09 to 14.14. And that is the confidence interval. So we are 90% confident that the true population mean number of hours worked during the Christmas season is between 6.09 hours and 14.41 hours. That would be our interpretation. I will write that formally as well. But the question be asked, does this interval relate to the population or to the sample? And of course it relates to the population, because we are using the results of a sample taken from the population in order to estimate the interval within which the true population average would actually fall. So the answer is, it relates to the population. It relates to the population. This interval that we came up with relates to the population. We are 90% confident. So this is our interpretation of the result now. We are 90% confident. We're 90% confident that the true population mean number of hours worked, the true population mean number of hours worked during the Christmas season, during the Yuletide season, is between 6.09 hours and 14.41 hours. Yes? And that is how we would interpret our result. Then the final question we're asked is to state the margin of error. As I would have indicated, the margin of error is whatever value comes after the plus or minus, after we have simplified at this stage. Meaning after multiplying z alpha over 2, which is the table reading from the standard normal table, by sigma over root n. Once we multiply out this section here, simplify and multiply, that value here of 4.16 would be our margin of error. So the margin of error of the interval is plus or minus 4.16. And that's the end of the problem. And I hope this was a very useful lesson for you in helping you to understand and appreciate how to calculate one sample confidence intervals for means. I will be doing future lessons on this topic as well as on confidence intervals for proportions. Until then, take care. Remember to like, share, and subscribe. Thank you.